let's finish up this handout, the Intro to Distributions handout. So much more to say, but for now this will be a good introduction. Number 2, here's how you'd usually say, and if you really think of this as a function, which we know is not really true, then one aspect of the fact that it's a spike only at 0 would be that delta of x equals 0 for x not equal to 0. Well, what does that mean about integrating? This is something that's closer to being meaningful. It means that if this thing is supported over here, then you shouldn't see anything. You should get 0. And so that's exactly what we say. We note that delta of phi, since that is phi of 0, that's totally going to be 0 if, it's really tautological, but it's important for later understanding about how this works, if phi of 0 equals 0. In other words, if the support of phi does not include 0. This little element, not an element. Okay, so and this is the picture, that if you have some phi over here and you act on it with this distribution that's supposed to kind of pick out the 0 part, then you're going to get 0. Okay, so this is really something that's easier to generalize to different distributions other than the delta function. That you put some condition on the support of your test function and you discover that your distribution will vanish on such a function. That means that the distribution is living somewhere else from where that test function is supported. So if that seemed a little bit trivial, it's only trivial for delta functions. Okay. Another thing that's pretty basic is, okay, let me just explicitly remind ourselves, okay, this integral, oh yeah, so really, back to ordinary functions. We will definitely come back to deltas. I wanted to do them in parallel because it's kind of weird to just constantly say, "Oh, we're going to look at ordinary functions in this new fancy way," and not talk about anything new. So I wanted to include the delta functions as early as possible. But remember, we had ordinary functions, and if we had like a function t, it happened to be big T because it was a temperature, okay? The way we make it act on a test function is we actually do write this, and now this is meaningful, because this really is an ordinary function, but we're using this new perspective. Now, for once, I'm going to put in the minus infinity to infinity, and as soon as you do that, red lights should go off, and you should be on guard for, wait a minute, this might not even exist, okay? So, remember, we don't want to put any really restrictions on big T if we can possibly help it. We want those to be super general and include deltas and all kinds of things that are weirder than deltas. And so our only choice to make this guaranteed to exist is we better restrict the support of this guy. So for example, if phi of x is just the constant function 1, if that's phi, and then you integrate it against some, I usually put their test functions in red. If that's phi, and then you have some test function that's not vanishing, that doesn't have compact support either, then this integral is almost certainly not going to converge. And maybe if it'll converge in a very tenuous way that doesn't have good properties. Okay, so we don't want that. And the draconian way to do that is insist that the support of phi is in a bounded region. Okay, so it's contained in some like minus m to m for some m. And the m can totally vary from phi to phi. It's not, we don't pick one thing off the bat and just say, okay, I have to be from -1 to 1 or -1 billion to 1 billion. That's silly. But it has to be compact, okay? So this is a closed, the closed isn't super important right now, but bounded is super important. A closed bounded subset of the reals, and that's called a compact subset. Okay. And so we're going to insist that the phi has compact support, which just means that it vanishes outside some finite interval. And we'll see later more generalized versions of compactness and that kind of thing. So we insist, let me just write it one more time, insist that all test functions, for now, phi, have compact support. And later we'll be in different contexts, we'll be able to relax that a little bit. Okay, but it's by far the simplest thing to do now, and it's the core thing of when we're defining distributions for the first time. Okay. So remember, they're also supposed to be continuous. We're building these restrictions on the test functions. Okay. Now, and if it does have compact support, obviously, just to reiterate, if it's supported from, say, minus m to m for some finite m, this is problem 4. This is all I mean in problem 4. Pretty easy. Okay. And now, this is continuous, and so that's not going to give us any problem for integration. And then, so all we really have to do is t, the only thing that has to be true about t is it has to be integrable with whatever theory of integration we have. So certainly piecewise continuous is going to work, and more. The cool thing, though, is that we've seen that even if we only allow t, if we allow t to be just piecewise continuous and not anything worse, we've seen how to take limits of those guys and create new gadgets like delta, which is in the spirit of this, but isn't literally defined by the integral of a function against a test function. Okay, so this actually avoids this method by going distributions pretty early. We're going to be able to postpone a lot of the finicky stuff about Lebesgue integration and how nasty can a function be and still be integrable. It'll be important eventually, though. Okay, so number 5, linearity. Okay, we haven't yet said what kind. We've said that a distribution, so it should be some gadget that takes some set of test functions. We still have to elaborate that more, but we've definitely done some good progress on that. They have to be continuous and compactly supported, and give a number. But is any possible function that takes a test function and spits you a random number going to be a distribution? I don't think so. That would really, literally, I mean, a function is an incredibly general floppy object. That would just say assign any completely random real number to any test function, totally unrelated. So if the test function doubles, it doesn't have to be related. Or if the test function like slides over a slight amount or something, it doesn't have to be related. That's silly. We've got to discover some rules for these mappings. And linearity is the first absolutely big one. Okay, and that's the fact that this, oh yeah, here we go, it's right here. If we put this in and we put in a combination, a linear combination of test functions, that's one thing you can do with test function, with any kinds of functions on the real line anyway. With real values, let's say, you can take a linear combination with constant coefficients, and it's absolutely fundamental for integration that constants and sums come out. That's going to be t of x. Let's make sure that's a t. Psi of x. Okay. Alrighty, so what that shows in a more elegant and formal language is that the result of t when you feed it phi, a linear combination of phi and psi, is exactly the corresponding linear combination of what happens when you feed it phi and psi individually. It says that this map from the set of test functions to the reals is a linear map. Okay, so this is where it helps to have seen in linear algebra the idea of a linear transformation, and hopefully the idea of linear transformation in a little bit of abstraction, not too much. Okay. Now, what's our only other example of a distribution so far? That's the delta distribution, defined by just what's the value at 0. And in fact, well, what the heck? Let's say at a. Okay. All right. Ooh, actually, let's say we don't want a because we're using a here. Let's say z. Why not? Okay. And that also has the same property. Not supposed to be hard. Okay. It's pure parenthesis pushing. By definition, this takes the function a phi plus b psi and evaluates it at the point z, but by definition of how you add functions and scalar multiply functions, that just gives you the corresponding combination of these guys. And wrapping it back up in the fancy notation, that is a delta z of phi plus b delta z of psi. So this also is a linear map from our space of test functions to the real numbers. Okay, so that's the reason for at the end of the handout, provisional definition 1 is a distribution on R is going to be a linear mapping. We are going to never want to do this in a nonlinear way. If somebody introduces a gadget that eats test functions and spits out real numbers in a nonlinear way, we aren't interested. That's not a distribution because it's not following the pattern of our canonical examples. Function thought of as a distribution and the delta function. And also requiring linearity just gives us access to all of linear algebra. It's huge. Okay, so we still need to say there's more restrictions on what the map has to do. We'll talk about next time. And there's more restrictions on what the test functions have to be. But we've got a good start.